Continuing now with the section 9.3 notes, we're ready to continue with example 6, part B. Here we have a system in 3 variables and 3 unknowns, a linear system. And we're told that the coefficient matrix of the system is identical to the matrix of example 5. What we're referring to here is when we write the coefficient matrix A for this particular system, looking at the coefficients of the equations on the left-hand side of the equal sign, that is the coefficients of the left-hand side of the equations, we see 1, -1, 0, 1, 0, -1, and 6, -2, -3. Also, we might just note that the matrix X, capital X, in this case would be XYZ, and the matrix capital B would be 4, 6, -4. What we were able to show in example 5 was that this matrix A had another matrix as its inverse, which we did not derive, but which was given to us and which we verified. So we will use that inverse, since the inverse exists, we'll use it to solve this particular system. And again, we'll use capital X should equal A inverse times B. The inverse from that previous example was the following: -2, -3, 1, -3, -3, 1, -2, -4, 1. B would be 4, 6, -4. A inverse is 3 by 3. B is 3 by 1. So because the inner numbers match, when you write the orders side by side, the product is defined, and the outer numbers, that is the 3 and the 1, determine the order of the product, which would again be a 3 by 1 matrix, just like matrix B, and which it should be because the matrix X, we know, is a 3 by 1 column matrix. So to produce this matrix X, we multiply A inverse and B. And let me show you what we obtain. 3 entries. For the first row, it'd be -2 times 4 is -8. We're taking first row with a column for B. -3 times 6 is -18, so plus -18. And then plus 1 times -4 is -4. For the second entry in the second row, -3 times 4 is -12. -3 times 6 is again -18. And 1 times -4 is -4. And for the third entry, using the third row, -2 times 4 is -8. -4 times 6 is -24. And 1 times -4 is -4. Okay, if we add these together, we get a 3 by 1 matrix, and this is what we would obtain. -30, -34, -36. Okay, well this represents the matrix X. So from this it follows that X must be negative 30, Y negative 34, and Z negative 36. That could also be expressed as the order triple, negative 30, negative 34, negative 36. So that is the unique solution to the system of equations in example 6b, found using the inverse matrix method rather than using something like, say, the addition method. Now, here again, it has to be admitted that it would really be easier to solve this system with, say, the addition method, but this gives us an alternative. And as we'll see in the next example, once we have the inverse of the coefficient matrix, if the numbers to the right of the equal sign change, we can use exactly the same inverse to find the new solution of the system. Whereas with the addition method, we'd have to basically start over. So now if we look at example 6c, we have another system of 3 equations and 3 variables. The left-hand sides of the 3 equations are identical to that of example 6b. So what that means is that the inverse matrix for this system is the same as the inverse matrix for the previous example. The only thing that's changed is that we have a different column matrix B because the numbers to the right of the equal sign, so we're talking about these, have changed, but the numbers over here are exactly the same. So if we use the inverse matrix method here, we use X equals A inverse times B with the same inverse matrix used in the previous example, that is negative 2, negative 3, 1, negative 3, negative 3, 1, negative 2, negative 4, 1, along with a new matrix B, 12, negative 6, and 8, from the constants on the right-hand side of the equal sign. And then we can multiply, just as we did in the previous example, to obtain a new solution for the system of equations. So let's see what we get. Let's once again write this out. For the first entry, it would be negative 24 plus 18 plus 8. Second entry, using the second row, negative 36 plus 18 plus 8. And then for the using the third row for the third entry, negative 24 plus 24 plus 8. Okay, that's going to give us negative 24 plus 26 is 2. Negative 36 plus 26 is negative 10. And then we have positive 8. We'll see this represents the column matrix XYZ. That is X. So it follows that X would be 2, Y would be negative 10, and Z would be 8. Or we can write our unique solution as the order triple 2, negative 10, 8. So that's the inverse matrix method of solving a linear system of equations. It requires a system it has to be a linear system with the same number of variables as equations so that you obtain a square coefficient matrix, and then the inverse of that coefficient matrix must exist. If it does exist, then the system of equations has a unique solution given by x equals A inverse times b. That concludes the notes for section 9.3.